we are going to talk about the SolidWorks CAM, which is the part of this series. And within that SolidWorks CAM, we are specific to 2.5-axis machining operations. In coming 2 weeks, inshallah, we're going to conduct a third webinar on reverse engineering. And we will also highlight the application of reverse engineering in the industries. Since we are authorized dealer, a reseller of SolidWorks in Pakistan, and the Quality Solutions has presence in 4 different countries around the world. In Pakistan, we have offices in Karachi as well as in Islamabad. And if you require detailed training courses on these topics, you guys can visit our office or contact us. So before I begin my CAM programming and the 2.5-axis machining operation, I want to revise the basics of the machines. There are 2 types of machines that we find often in the workshop. One is the turning machine or a lathe machine, which include mostly 2 axes. The x-axis of that machine allow the tool post to move in a direction which is perpendicular to the direction of the axis of rotation of spindle. Whereas the y-axis in lathe machine allow the tool post to move in a direction which is parallel to the axis of rotation of the spindle. And the lathe machine is also called the mother of all machines. And if we go for the milling machine, it's a little bit difficult as compared to lathe machine. We have more access of freedoms. So here, our typical manual milling machine includes 3 axes that we can find in workshop. But if we have, let's suppose, the international brand milling machine, then it can also have 4th and 5th axis. The x-axis is along the length of the table, in which the table of the milling machine is you can see on the left-hand side, the picture we have, this is the milling machine. So the x-axis is along the direction of the length of this table, and this table is allowed to move in x direction, whereas the y-axis is along the width of that table, and the z-axis allows the table to move up and down. In case of 4th axis, A-axis, the spindle or the head of the milling machine is able to tilt down or tilt upward about this specific pivot point. And this head is also able to rotate toward the left and right about these axes. And we can see a silver scale which has a marking of degrees, which shows how much degree we have to rotate this spindle about this specific axis. So these were the manual machines and the axes in those manual machines. So let's jump to the CNC machine. The most fundamental of CNC machines are 2.5 axis and 3 axis. And what 2.5 axis means? It means the cutter of the milling machine cuts the material or remove the material in only 2 axes simultaneously, either in XY plane, YZ plane, or ZX plane. So it's called a 2.5 axis CNC machine. If we go for 3 axis, we can perform the machining in 3 axes simultaneously. So if we go for a little bit higher end, we will have 4th and 5th axis index machining along with the 3 axis simultaneous. What it does, it basically it rotates the workpiece to a specific degree based on our requirement, and then we can perform the 3 axis machining operation on that workpiece. Same goes for the 5th axis. The most higher end of CNC machines are 5 axis CNC machines, and these are removing the materials in 5 axis simultaneously. And we will hopefully cover these machines in upcoming webinars. So for this webinar, we are constrained to 2.5 axis machines. So the CAM is basically the abbreviation of computer-aided manufacturing or computer-aided machining. It requires a software and a computer to generate the G and M codes, and which will automate the machining process. So it usually involves three basic fundamentals. We must have a CAM software on which we can generate the G and M codes. And we must also have a relevant post processor which convert the programming into G and M codes. And this post processor is relevant to the type of the controller we have in the workshop on the machine, CNC machine. And thirdly, we require a CNC machine for performing the actual machining operation. If we go a little bit in detail about how a part is finalized from the concept to the final product, in case of machining, we can start with the 3D CAD modeling, in which we perform the detailed 3D drawings and 3D CAD modelings. And we then perform the simulation on that 3D CAD part to validate whether that part will perform in the actual world or not under certain conditions. Once we have finalized the design of 3D CAD model, we can start the machining CAM process, which in the end generate the tool path. So with the generation of tool path, we can go for the generation of G and M codes. And this is the language of the controller that CNC machine controller understand. So, and these controllers, the format or the codes in a text file will be sent to the controller of the CNC machine. And the controller will then send the signal to the motor driver, which will send the command or signal to the motor. So in CNC machine, for high accuracy, mostly the servo motors are used because it is a closed loop, and it gives us the good accuracy as compared to a stepper motor or hybrid motor. So with the help of these motion of the motors, we can get the machining process, and then in the end we get the final product. So there are some fundamentals of machining parameter that we must be aware of. Either we are performing the manual machining operation or the CNC operation. And these parameters are called, some of them are here. The most basic one is surface speed, the spindle speed, and the feed rate. Mostly the surface speed is provided by the manufacturer of that tool that we are going to use in the machining process. So the surface speed depends on the material of the tool, the size of the tool, and how it has been designed. So, and this information is mostly provided by the manufacturer. So with the help of this surface speed, we find out the spindle speed in RPM, to what speed the cutter must rotate. So we will get this, use this formula and find the find the spindle speed. And then we can also use spindle speed information and the cutting speed to find the feed rate. At what speed the workpiece should move along with the rotation of the cutter or against the rotation of the cutter. So, all right, so here we have the basic CAM workflow, in which it shows from where we have to start and to what stage we have to end. And this is specifically for the CAM. It's all start with the part modeling. We have to design a 3D CAD model in the SolidWorks, or we can also import the CAD model from a different software. If we have Creo, if we have Inventor, or CATIA, we can import that CAD file into this SolidWorks. And then we can use the SolidWorks CAM tab, or we can also use the CAM work. I will also talk about the CAM work a little bit after some time. And basically, it is the golden partner of SolidWorks, and they developed the SolidWorks CAM specifically for this SolidWorks. All right. And then we start the real settings with the machine, in which we select what type of machine we have to use and what should be the parameter. Then we go for the size of the stock. the material of the stock, and then we'll perform the, we will extract the features that are required to machine the stock material. And these features will be helpful for us to generate the operation plan. So we can adjust the operation plan based on our own order, which steps should go first and which steps should go at the end. And then we generate the tool path. So we verify the tool path with the help of a simulation. And if the tool path is not correct, we go back to the adjustment of the operation plan and then regenerate the tool path. So once the tool path is finalized, we can start the post-processing, and then we will receive the extract the text file, and this text file will then send to the controller. So here the CAM process will end. All right, so let's talk about the demonstration. So we have a SolidWorks here, and I have also imported the CAD file of the voice on which I have to perform machining, and this voice is called Kurt Voice DX. You guys can download this CAD file from the internet as well. It's available there. So I've also made some customization in this stage. I have created a 3D sketch which will be used for the stock materials, and this 3D sketch have some constraint with the jaws of the voice. So we have the red color jaw, and the bottom sketch is in constraint with the jaw, as well as the talon. You can see there are two talons on these two jaws. So this sketch will be helpful for us to resize the stock material based on the final CAD file that we have to achieve. All right, so I have also created some of the planes in these sketches. Here you guys can see the bottom sketch is in constraint with the talons as well as the jaws of the voice. I have also created the planes which will be used for the reference to specify how thick the stock should be. All right, so I will show you how to use this information for the CAM process. All right, so let's look at the CAD file that we have to perform machining on. And this is the CAD file, and we want to machine a part, and it should give the result in this design and this shape. So before we begin the CAM process, we have to analyze what type of features are there in our CAD design. We have pockets, and there are almost 6 pockets we have. We also have some bosses in our design along with the chamfers. So we must also know the information about these features, like if it is the chamfer, then how much degree this chamfer has. It has 45 degree and it has a thickness of 1 mm. Same goes with the other features such as the fillet, and these fillets are of size of 3 mm in radius. And we also have the bottom fillet, which is also a 3 mm. So before I begin the CAM process, we first analyze this CAD file, and we can see here we also have holes, and these holes are thread holes, and the information of these holes are also shown here. The smaller holes are M7 times 1, and M7 is the size of the bolt and 1 is the size of the pitch. So there are 2 holes of this specification that we have to machine. We also have a bigger hole of M10 times 1.5. So 1.5 is the pitch and the M10 is the size of the bolt. So based on this information, we have to select what type of tools we require. Do we need a ball nose? Do we need a flat end mill? What should be the size of the drill bit? And what should be the size of the cap? This information must be gathered at the start of the process of the CAD. So whether we have to buy the some tools from the outside, or it is or these are available in the workshop. So let's import the CAD file from the part modeling to assembly modeling with a simple click. And let's increase the workspace a little bit. All right. So with the left click of the mouse, we can drag and move around the part. So let's press the click and move around. And with the right click of the mouse, we can rotate that CAD file about any specific axis. So it would be easier for us to change the orientation of the CAD file. So let's start some constraint on this CAD file. So make sure that the bottom face is completely aligned with the upper face of the jaws. So for the bottom face, we have to select the bottom face. We can also use the Alt button, which will hide the front face. And it will show us the faces which are at the behind. So let's press the Alt button, and then we will have the display of the face of the bottom. So we can just simply click that face. All right. So this is the first phase of the CAD file we have to constrain. The second reference level is also shown in the shortcut, and I have already created a bottom of part. So once I click it, it automatically moves that part to this specific reference. And as you guys can see, there is some clearance between the bottom face of the part and the upper face of the jaw. This is because if we have to perform the machining, we have to make sure that there is enough material left at the bottom, which would be used for holding the stock part between these two jaws and the talons. All right. So let's say if I want to change the orientation, I press the right click of the mouse and rotate this part. So if I go for the top view, I can press the right click and move my mouse in the upward direction. It will show me the top view of the CAD file. So with a simple click, I can drag and adjust the file in a position I want. So in SolidWorks CAM, we have additional add-on which is used for resizing the stock sketch. So this is a sketch and it's not completely enclosing the whole CAD file. So in SolidWorks CAM, we have auto size stock. With a simple click on it, it will resize the 3D sketch of the stock that we have to use. So it's very easy to use, and such type of setups will save a lot of time if you want to perform CAM operation on multiple parts or one after another. In this specific orientation, the jaws are not in a position to hold that stock material at in a firm way. So we have to move around the parts and change orientation so that the jaws can able to hold that part firmly. So this position is much better. All right, so let's go to the top view. All right, we can perform the constraint so that the front face of the CAD file must be parallel to the sketch line. So we go to the assembly, select the map, and click the front face, and then we will click the line of the sketch so that the front face is coincident with the line, and it is also parallel along the line. All right, so this orientation is much better. We will press the auto size stock. It will again resize the 3D sketch of this stock. So if we look at from the top view, we can just simply drag and move around the part so that make sure it is in between the 3D sketch. All right, so we can see that jaws are not long enough to hold that part. So in SolidWorks, we have options of configuration in which we can and see what type of jaws we have. So if we press, we can find out we have a jaw of 8 inches of length. So we'll select this one and click OK. So the jaws has been extended. We'll perform the same operation for the second jaw. And now we have two long jaws, which are good enough to hold that part. Now we want to increase the number of the talons. Talons are a great tool to hold the stock material firmly. It's quite easy to use and disassemble. We can press the control button and make a copy of that part of these talons. So press the control button and click that part and simply drag and drop to the position we want. It will also create the assembly mate with the holes that are created on the top face of the jaws. Similarly, we will also create the copy of the other talons. So we will have enough number of talons to hold the part firmly um, at a specific location. All right. So the settings for the assembly and fixtures has been completed. So we will jump to the second step, which is the machine setup and the stock setup. So in SolidWorks CAM, we have different type of tabs. One we can see here, this is called Operation tab tree. Feature tab tree. We also have Operation tree as well as Tool tree. So there are three tabs that are related to SolidWorks CAM. And within the feature tree, we have the options for the machine in which we can select what type of machine we need. And we can also adjust the parameter of these machines. In the command manager at the top, we also have icons to define these machines. So we can also select that icon from the command manager. So let's define the machine, what type of machine you should use for the CAM operation. So in the dialog box, we have some tabs that are relevant to the type of the machine. And these are the machine tab, tool grip tab, and post-processor tab. So under the machine tab, we have option of mill metric. And this is the 3-axis machine. So we will select this machine. And then in this specific machine, we have further categories, whether this 3-axis machine is heavy duty, light duty, or medium heavy duty, which in return defines how powerful is the motor of the spindle and what is the size of the bed of the machine. So for this webinar, for this demonstration, I will select medium duty. And then under the tool grip, I have also created custom design tool grip, so which includes all the tools required to machine this part. So I click this tool grip and select. So we have the information at the top about the different type of tools we have. So if we look at the CAD file, we can find out we require certain type of tools for certain features, such as in this case, we have a pocket and it has a corner radius of 3 mm. So that we must have a flat end mill of a radius of 3 mm. So the diameter should be 6 mm. So if you want to achieve the high accuracy and get the final product same as the CAD file, we must have the flat end mill of size of 6 mm. Same goes with the other features. There are some fillets, and these fillets, this specific fillet require a corner round type of tool, and it has a radius of 3 mm. So if we will use this tool, it will create the fillet of 3 mm at the top face of the boss. And we also have the bottom round corner, which require a ball nose, and we have a 6 mm of diameter of that ball nose. It means it has a radius of 3 mm. So let's see some other tools we have. We also have a tapping tool for the machining the thread. So if you look at the holes, we have two different size holes which require two different type of tabs. So one is the M7 time 10, one M7 time 1. One is the pitch. So it requires a tab of M7 time 1. So we have already in the tool grip. And the second hole, a thread hole, require a tab of M10 time 1.5. And we also have in our tool grip. For the chamfer, we also have a countersink to create the chamfer. Let's go to the post-processor tab. Under this tab, we have various controllers, library in the SolidWorks CAM. For this demonstration, I select the male Fanuc 16M. We can also import the post-processor library into the SolidWorks CAM. So under the posting, I will leave these two options as it is. I won't change these two options. So we also have some information about the part thickness, and this is the thickness of the stock material, and which will be helpful for us for the generation of the setup sheet. So if we want to confirm whether we have a stock of this height or not, we can go to the evaluate tab and select the measure icon and then click on this line. We will have the length of 25.4. So this part thickness is also 25.4. So it's correct. So since we are using 2.5 axis machining operation on 3-axis machine, we don't require 4th or 5th axis index machining. Therefore, we won't use some other tabs like we have a rotary axis or tilt axis. These two tabs are used for 4th and 5th axis index machining. So we will leave it unchecked, these two. Click OK. So we have completed the machine setup. Now it's time to select the type of the the CAD file that we have to machine. So we will right click the part manager and select the type of the CAD file we have to machine. So here in the workspace, we have various CAD files. We have assembly, we have JAWS. So we have to select the CAD file. So make sure that machine understand that this is the only file that requires machining process. It's also mentioned here with a number, which is specific to this CAD file. So thirdly, we will select the type of the stock. So we have different type of materials in the library we can select. So in this situation, I will select the aluminum since it is soft and can easily be machined. So this stock type, so how we can define the shape of the stock. In SolidWorks CAM, we have 4 different methods to define the shape of the stock. In the first one, we have the bonding box, which actually create a box which will envelop the CAD file in it. We also have extrude sketch, in which we can select the sketch and then specify the reference to what height that sketch should be. So we will select the sketch which we have already made in the beginning, and then I will specify the height of that sketch to extrude, which would be the stock material for us. All right, so here we also have the stock size in X, Y, and Z direction. We have 266.7, Y is 88.9, and Z is 25.4. This information is very crucial for the CNC machinist, because if you use this stock material other than this size, then there would be chances to have accidents during the machining operation based on the current CAM programming. So here we have finalized the size of the stock as well as the material. Lastly, we will select the coordinate system. So simply we can go for the stock bounding box vertex, in which it shows various vertex on the stock material. And for this demonstration, we can select the center vertex of the upper face of the stock. And it also shows the z-axis direction and the x-axis. If the z-axis in the upward direction, it means when the z is positive, the tool will move in the upward direction, and if the z is negative, the tool will be moved in the downward direction. The x-axis and y-axis are also specified. We will leave it as it is. So the second step has also completed. Let's jump to the third step, to extract the machinable features. So in SolidWorks CAM, we have intelligent type of feature. It reads the CAD file, it extracts what features are there on that CAD file, and then generate the operation plan and tool paths which we required. So it will save a lot of time. The option, and then under the mill features, we have information about the extract machinable features. So what type of features this SolidWorks CAM will extract? So we have checked these features: hole, non-holes, bosses, face, parameters. So these type of features on a CAD file will be extracted by the SolidWorks CAM automatically. So we have checked it. So let's start the AFR, which will take maybe around 5 to 10 seconds to read the CAD file and generate the features for the CAM. All right. So under the feature tool tree, it has extracted various type of features, and it also created a setup for the machining. So under the part, we have two setup, and these are setup 1 and setup 2. And these two setups are required to completely machine the part to achieve the final result of this CAD file. Whereas we have another setup which is below the part manager under the machine. And this is the setup that will tell us that these are the operations we have to perform in the current setting. Since we have a vise, we have a fixture, we cannot start performing the machining from the bottom of the part. So this setup will show us we can only perform the machining at the top of the part of the CAD file. So here we have face feature, we have circular pockets, irregular pockets. So these are the irregular pockets. We have almost 6 irregular pockets, and all of these pockets are extracted. We also have oblong pocket for this punch-like shape. And then we have the pocket at the bottom, which is go-through pocket. And then in the end, we also have holes. This SolidWorks CAM, the AFR, only extracted two holes only, and it did not extract the third hole, which has a size a little bit different from these two holes. There can be various reasons why it did not extract the third hole. Either the settings were different. So for that, no problem, we will create the manual operation on this third hole to create the center drill, and the tapping. All right, so once we have all the operations by the AFR, we can jump to the operation plan, and then generate this operation plan. All right. So here under the operation tree, we have, all right, so I forgot to talk about the way these icons are organized. So we can see these in SolidWorks CAM, the icons are organized in a tidy way from left to right. For those who are newcomers and new users, and they can just simply follow the step from left to right, and they will get the result. We can, from the extract, we can press the generate operation plan, and then generate the tool path. And in the end, there is also an icon of post processor, which we can press in the end. So it's quite in an organized way. So under the feature tree, we have these features that were extracted by the AFR, automatic feature recognition, and we also generated the operation plans for these features. We can see we have the face mill operation plan for this face feature, and then for the parameter, we also have operation plan for parameter. All right, so for the face milling, we have the specific tools as well, which will be used for the machining, which is T09. This is the tool ID, and the size of the tool is 50 mm. So for the parameter, we have the rough mill and the control mill. So here we can see we have parameter, which is open pocket, and it's also specified with the strategy. And these rough and finish, it shows this strategy that how we have to achieve this result. So first we require roughing, and then it will require a finishing operation. So there are two strategies involved to achieve the parameter result. So if we look at, I will also tell where the solvers can select these strategies automatically. So far, we haven't selected any strategy, whether we want only finishing or whether we want coarse or fine. It just, as a default, is selected rough and finish strategy. So all of the operation plans of the features are shown here. Rough mill for the parameter, and we also have control mill for the controls. There are a lot of operation, and we want to organize these operations in an order way. So we have this option, sort option. Under the sort tab, at the top we have a face mill. So we will keep the face mill at the top. So make sure it is the first operation of machining. Then we will drag the rough mill from bottom to the top under the face mill. Same goes with the control mill. And then when I will press the OK button, these operations will be organized in this specific order. First, there will be face mill, then there will be rough mill, all rough mills, and then there will be control mill. And rest of operations such as center drill, and counters, they will be at the bottom. So let's press OK, and then we can see the operation have been organized. So we have at the top face mill, followed by the rough mill, and then the control mill. Now we will generate the tool path of all of these operations. We can see here the color of the operation plan turned from blue to black. The black color means we have operation along with the tool path, and the blue color means the tool path of this operation has not been generated. There may be some reasons, either the control milling is not removing the material, additional material, or the size of the tool is bigger to perform this machining operation. So this specific operation is used for circular pocket, and we can see there is a gap between the outer edge and the inner boss. So, and this 20 mm flat end mill is quite bigger to fit in between these two spaces. So let's change the tool and select the smaller one. So we will go to the edit definition, and under the tool, we have a tool grip. And here we have already defined flat end mill of size 6 mm. So we will select this one, and we will also use the corresponding holder for that and click OK. So let's generate the tool path for this specific operation. And we can see that its color has turned from blue to black. It means now it has the tool path. All right. So all of these operations have tool paths, and let's see the simulation, how this machining process will be carried out. So in solvers, we have a simulator to see how this tool will move and remove the material. So let's press this simulate tool path. We have some controllers. Here we have controllers under the simulate tool path. We can change the speed of the tool moving around and removing the material. We have also some show difference type of features to compare the result between the machine part and the CAD file. We can also have section view in which we can see the CAD file, the stock material in a section way. So we don't require this feature right now. So, okay. So under the mode, we have two different modes. One is the tool mode and second one is the turbo mode. The tool mode, let's run the simulation under the tool mode at a little bit slow speed. So we can see the face operation is being carried out at the top of the face, and it's removing the material in steps. It takes a small cut and then it's remove the material. So if we change the mode to a turbo mode, we will see the final result without wasting some time on looking at the simulation of the tools. So let's play the button and we will see the final result. Here we have the final result. So in the final result is also coded with the colors, and these colors have information about machining process. The blue color you guys are seeing on the front face shows that the machining is not done on this area since we don't require machining, and the red area shows there is a collision of a tool with the material of the stock. So either the tool is tracking, or in the rapid mode, it is colliding with the boss of that material. The rest of colors shows the orange color shows the contour milling operation, and the green color shows the rough milling operations. So these colors are quite helpful to understand which operations are carried out on which area. So we will change the some settings in order to avoid this collision of the tool path with the material. All right. So here we have already generated the tool paths of the operations. And if we look at these operations, we will see the type of the tools at the front. It's 6 mm of flat and milling tool cutter. And these operations, rough mill 4 to rough mill 10, all of these operations are using the same tool cutter. So in order to make it precise and easy to use, if you want to change the setting, what we can do, we can select all and combine all these operations. So if we change the setting only in one operation, it will change the settings to all of these operations. So it would be helpful for us to make changes in the end, since all of these operations using the same tool of 6 mm. All right. So the other tool operations, they have some different features. We cannot combine them because if you want to make some changes, it would be applied to all of these two features. In case of rough mill, for the perimeter, we have an option of machine island top. So we will uncheck it, and what it does, it will create the tool paths only at the sides of the part. But in this scenario, there are some tool paths at the top, and that it also generated. So later on, I will change this information. I will recreate the rough mill operation by recreating the perimeter. All right, so let's simulate after we have combined various operations. We can look at the simulation in a tool mode, where we can see how the tool is removing the material from the stock. This is the perimeter operation in which is moving the material at the boundary of the CAD file. One more thing we have noticed is during the parameter operation, it completely removes the material to the bottom, which would be a problem for us. So how to hold that part between the two jaws. So we have to specify the end conditions as well under the parameter feature. So let's try to concise further operations of these mills, control mill from 4th to control mill 9. Let's combine these operations, 6 operations, into a single one, which is using same type of cutter. All right, so from the list of so many operations, we have reduced to only few operations, and which would be easier for us to control these information. So whenever we perform the change in the operation and in the toolpath, we have to go back to the simulator to perform the simulation to see the end result. Whether it is performing in an order as we required, or it is colliding with the material, or it's not performing as we want. So as I've said, in case of the parameter, is to move the material also at the bottom. So we have to change the end condition of the parameters. So here we specify the bottom of the part. So now when we perform the machining, the tool will only remove the material till the bottom face of the CAD file, not the stock part. So we will have some extra material left at the bottom, which will be used for holding this stock file. So let's regenerate this parameter information. So it again created the operation for the parameter. We have roughing as well as we have contouring. So we'll simply click and drag that roughing under the face mill, and then generate the tool path, go back to the edit definition, and we don't have to machine from the top. So we will uncheck the machine island top. So it will not perform machining operation at the top face of the CAD file. And on the screen, you can also see some of the tool paths have been removed as well. So we have also generated the tool path for the control mill. Now we will perform the simulation and see the result. Since we specify the end condition of the parameter, and it must leave some material at the bottom, which will be used for holding that stock material. So far, everything is going fine as we require. All right, here we have a problem. We can see there's a red region shows at the top face of the part, which means that tool is colliding with the part while it is in the rapid mode. So we have to assign some retract limits. So in the rapid mode, it must go to the top. And then in a clearance mode, it should also go to the top of the stock with a distance of 5 mm extra from the top of the stock material. So whenever the tool will retract while jumping from one operation to another, it will follow these two criteria, and so that it won't collide with the other materials which are not being cut yet. So we have to, once we apply this information in this setup, we have to apply manually to all of these rough operations under the NC tab. So let's right click, go to the edit definition, and then under the NC tab, we have the setup definition option. We will select this one. So it will use the information that we have specified in the first step of the setup. So we have to apply these information to all of the roughing operation. So none of the tools should collide with the material while performing machining. Another way is, instead of using this safety precautions for all of operation, we can identify which specific operation is in collision with the material, and then only select the settings for that specific operation. So let's see the result. We have applied the settings to all of the roughing operation. Let's simulate it and see the result, whether it is colliding with the material or not, the tool cutter. So we go to the simulate, and in the simulation we have option the next tool path, in which we will have the simulation of a single tool path only, and it will stop and it will show us the information about that tool operation. What is the name of that tool operation? We will play again, and then it's performing the machining operation of rough mill 11. So far it's going fine. Tool is not colliding with the material so far. So we have extra material left at the bottom, as I've said earlier. We will play again, and then next operation is now being performed, and there's no red region shown by the color. The rough mill operation for the irregular pockets, the second pocket, third pocket, fourth pocket. So everything is going fine. There's no collision with the material. So earlier, the rough mill operation had a collision with the material. So far, it's perfect. All right, now the second step has been started, which is the control milling. We haven't specified the setup definitions in the control milling, so it might collide in this stage. Let's play the control mill 2. Yeah, at the stage of control mill tool, control mill 2, there's a collision of a tool cutter with the material, and it is highlighted in a red color. So we have to stop the simulation, go back to the operation, and then select the settings of the setup definition. So it was the control mill 2. We will right click and go to the edit definition. Under the NC tab, we have to select the same option as the rest of the features and operation. So click OK. And then start the simulation. So I will select the turbo mode to save time. So in a few seconds, I will see the final result, and there is no red region in the final result. So there is no collision while simulation, and everything is going fine and as we want. So as I have said earlier about the technology database, and that is the brain of the SolidWorks CAM. So you might be wondering that these operations have information such as the spindle speed, the feed rate, the type of the tool, and the material of the tool, and everything has been selected automatically, and we haven't changed anything. So how this SolidWorks CAM identifies such information by itself? The answer to this question is there is a database. It's called technology database, which have the library. So let's open this technology database. This technology database is powered by the Camwork. As I have said earlier in the beginning of my presentation, the Camwork is the golden partner, and they developed this SolidWorks CAM only for the SolidWorks. For the advanced machining, we can also have Camwork features for 5-axis, for milling, for mill and turn, for ADM, for additive manufacturing as well. So Camwork is providing advanced solution in machining. So let's see, under the machine, we have three columns. One is the machine column, second is the strategies column, and the third one is the tool crib. So under these columns, the information had been fed up. So let's open the mill metric, which is the 3-axis machine. Let's see what type of information we have. So in this 3-axis mill machine, it is assigned with the specific controller. It is also assigned with the type of the motor that this machine have. It has 30 horsepower of motor. What should be the maximum feed rate for this machine? The maximum rapid rate? What would be the size of the bed of this machine? And also the spindle speed, which is 12,000 RPM. So the information that was generated by the AFR automatic feature recognition, it takes the information from this database. And similarly, for strategies, if we open up the feature and operations, we have strategies. And here we can see the AFR, it find out the operations and features, phase features, parameter, open pocket features, and it specify the rough and finish strategy automatically without our own interference. So let's see how it selected that strategy. We will select the feature, open pocket, and then see the strategies. So under this feature, we have maybe around 6 or 7 different strategies, but the SolidWorks CAM only selected the rough and finish strategy. The answer is we have selected it as a default. So let me show you. I will open up this strategy, and here we can see this rough and finish strategy is checked as a default. So whenever there is a parameter for open pocket operation and a feature, it will have the rough and finish strategy as default. So that's how it's extracting the information, and that's why I said the technology database is the brain of SolidWorks CAM. Under the strategies, we have other options like how big the part can be, which is around 1 meter in this situation. We also have information about the tool, what type of tool should be used for this parameter operation. Either it is ball nose or flat end mill tool, and then also the all of this information. So under the tool crib, I have customized my tool crib as I've said, and here you guys can see the station numbers, the tool IDs, as well as all the tools that I have used in this machining operation. So these tools have the information in terms of tool ID as well. So let's say if we want to add a new tool, I can just simply click the add button, and then we have another option we have under this add option is user defined. What we can do is we can design our own tool and then import into this technology database. So which we can be used in this tool crib. So for timing, I will select this flat end mill, and it will open up the library of the flat end mill. So we have a list of all the flat end mills in our library. It starts from smaller to the bigger dia of the flat end mill. So let's, for the example, just for the example, I will select the 25 mm diameter flat end mill. And it has information as well that the shank is straight or tapered, what should be the diameter, what is the overall length of this tool, the flute length, how much this tool is extruded out is also specified here. So let's use it as a default. It also shows here the type of the material. You can select the carbide or the high-speed steel. So let's select this tool. It shows under the tool grip. We can specify the station number. So let's say we will write down 10 for this one. All right. So I don't want to use this front end mill for my machining operation, so I will delete it. I was just showing you how to add a tool in the tool grip. Okay, these were the information relevant to the milling operation, the machine setup, the machine information, the strategies, as well as the tool grip. So let's talk about the feed and the spindle speed. In technology database, we have a different section for it. And if we open up a feed and a feed rate editor, we can find a library of materials. So this is the material list library. It includes most of the materials that require machining, stainless steel, steel, aluminum, cast iron, along with the speed and the feed for this specific material, and the type of the tool we are using, and what operation we should use, 2 or 3 axis roughing and milling. We have a complete chart of the feed rate and the spindle speed based on the depth of the cut. If we increase the depth of the cut, the values will decrease and change. So these charts have already been developed with the help of a software. We can make our own chart as well. So, and I think this was the basic introduction of technology database and how servers can use that database to generate the operation and the features automatically, along with the strategies and the spindle speed and the feed rate. All right, we have created the machining operation, and this CAD file is held between the jaws of the vise. But how we are sure that the tool path is not in collision with the jaws and the talons on these vice? So for that, we have to specify that these vice and the jaws and talons are the fixtures, and we must avoid machining these two components, these parts. So we go under the setup parameter, and under the fixture tab, we have the option here. Here we can select which CAD file is used as a fixture. So now we will select the jaws. First, we will select the talons, and we will click on it and then add all instances. Since it is the copy of the original file, so it will adapt the copies, all the copies, and there were 3 copies of that talon. Similarly, we will do the same process for the second talon, and also we will select the jaws of the vise, both the back one and the front one. So these are the fixtures, and we have to avoid machining these components. So for that, we will click avoid all and click OK. It will ask us to regenerate the toolpath. So we will let it to regenerate. It will take some time, maybe around 10 seconds. Okay, the tool path have been updated, and we can verify by seeing the simulation. Here we can see in this simulation we have the fixtures as well. If the tool will collide with these fixtures, it will be highlighted in the color. So let's start the machining operation, and we can see it's performing the parameter, and it's leaving at the bottom some material that will be used for holding that part. and then it's performing the roughing operation at the top pockets. Now the contouring operation. All right, so I think if we continue the simulation, we will find out that there's no collision of the tool with the fixtures. All right, so the next step is to, to generate our own operations and features on areas which were not identified and extracted by the AFR, such as we have the round fillet at the bottom, we have a fillet at the top of the face, we also have these thread holes that are not been machined yet, not been programmed yet. We also have chamfers. So let me show you how to use a manual method to generate the operations and tool paths step by step. So under the feature tree, we have a mill setup. We will right click and then select the 2.5 axis features. Now we have to select the profile that we have to perform machining in. So once we click the edge, it will automatically select the complete loop. We will use the outer edges of both of these oblongs at the left and at the right. Okay, we'll go for the end condition here. We will specify what strategy we have to use. Until now, we haven't specified the strategy, and in AFR, it was selecting the strategy by its own, as we have mentioned in the technology database. But at this point, we have a freedom to select strategy. Either we want to select the coarse, fine, finish for this specific operation. So I will use the rough and finish strategy. It also shows what type of tool will be used, the tool ID, the tool diameter for this rough milling operation, and the contour milling operation. It gives us the idea about the strategy. So for the end condition, here I will specify to what depth we should perform machining, from the top edge to the bottom. So here I select the vertex and select the vertex point to specify the depth. So let's generate the operation plan for this feature. So we can see we have two operation plan for this specific feature, pocketing feature. We have the rough mill and we have the contour mill. And these are shown at the bottom. So and the color is also blue. It shows that we don't have the tool path yet. So once we will regenerate it, it turns into black color. And we can also visually see the tool path. So now just click and drag and drop that rough in the rough mill section. Same goes with the contour mill. So let's simulate the result in the turbo mode to save time. As I have said, whenever we have created some operation, we have to go for the simulation process to verify. Here we can see it has removed the material to a certain depth, and we have to further perform the machining. So let's create another feature of 2.5 axis. We will select the pocket and then select the outer edge. So it will automatically select the closed loop. We will do the same for both of these oblong faces. And now we will select the strategy, same rough and finish. And then to what depth we have to specify machine. So I'll use the vertex and specify the height, which is same as specifying the depth. So here I have specified the depth or the height of the machining. So let's click OK, generate the operation plan of this feature. Here we have two plan, rough mill and the contour mill. Let's generate the tool path of both of these two plans. We will select both of these by the control button, and then we will generate it. So drag and drop this rough mill under the roughing operation, and then contour mill under the contouring operation, and then see the result with the help of simulation. So we will select the turbo mode and see what additional machining has been performed. So we can see another pocket at the bottom, and there is a step as well. So at the corner, we have some material left, and at this area, we have to use a different tool. So it will create the bottom round fillet as well. So for that type of machining, we require a ball nose type of tool. So let's create the feature. Again, go back to the feature tree, select the 2.5 axis and the outer edge that we have to create the fillet. So I think the top edge is better to select. So let's select the top edge of the fillet. Same goes with the other bottom round fillet, and go to the end condition. Here we have to specify the strategy. I will select the finish strategy, so it will only use the contouring operation. I will specify the depth. So this fillet will be created since it is coincident with the bottom face. So let's generate the operation plan and the tool path. All right, before generation of the tool path, I have to select the type of the tool, as I have mentioned earlier. So under the tool crib, we have a tool of ball nose, which have a radius of 6 mm. So this, I will select this tool, also the corresponding holder, and click OK. And now I will generate the tool path. Sorry, I mistakenly selected edit definition as well. All right, yeah, sorry, I have to specify the corner. Since it is a corner round fillet, so change the radius to 3 mm, and then bottom finish as well to have a good finish. And now generate the tool path. Drag and drop under the contouring section. We can see the tool paths as well. So we will drag and drop and then simulate in the tool mode method. So let's see the simulation. So the perimeter operation is being performed here, removing the material from the outside. Now the roughing operation, pocketing. Yeah, now the contouring has been started as it shows in the orange color. We have a pocketing, and now it's creating a pocket, and there we go, where we can zoom and see the round fillet. Since we are using the ball nose type of tool, and when it will perform the machining, it will create this type of fillet. If we compare the result with the original CAD file, the green portion shows that the green area is exactly what we require. And the blue portion, the blue area shows we have to remove the material from that area. So, so far everything is going fine and perfect. So in the next step, we will remove this blue area by machining operation such as the filleting and the chamfer. So let's start the filleting and the chamfer. So I think I will take some time to create a poll to get a survey. Let me launch a poll. Here we have a question, and it's a which engineering discipline you belong to. Try to answer these questions as fast as possible, so we will have enough time to further explain the machining operation. So only 42 people right now have answered the question. So can you guys please speed up the process? All right. Can you answer which engineering discipline you belong to? Mechanical engineering, electrical engineering, or civil engineering? If your discipline is not in the answered section, you can select the other option. All right, time's up. So this is the result. I think you guys can see on your screen. We have here 40% of the attendees are mechanical engineer, and then 20% are electrical, and then 25 is also civil engineers. The rest are from the electronic or from the other department. Let's create second poll. All right. So the second question, what CAM software you use or are aware of? So kindly please answer these questions. If you are using SolidWorks CAM, you can select the CAM option. If you are using Master CAM or a Power Mill, please do select the answer. The Fusion 360, Creo, Hypermill, or if there is another software that you are using in your company, you can please specify and select in other section. All right, let's end the polling and let's share the result. Here we have the result. So 52% of the attendees are using SolidWorks CAM for the generation of the CAM process. And then 8% of them are using Master CAM. Some of them are using Power Mill. 5% are using Fusion 360, and 12% are using Creo. So it's great. All right. Let's continue the webinar. All right. So let's start the filleting and the chamfer. Since the AFR has not recognized in these top fillets, we have to select them and generate them manually. For that, I will go under the feature tree manager and then select the mill part setup, 2.5 axis features. And in this situation, I will select the boss option. Previously, I was using the pocket because pocket removed the material from the inside, and it will remove, keep the material at the boundary. But in case of boss, it removes the material from the outside, and it will keep the material in the inside. So since we are using the fillet on this boss, I select the outer edge of this boss, and then we specify the strategy. I will leave it as finish. It shows the control mill operation as well. And then I will specify to what height I have to use this machining operation. So I will specify the upper face and then generate the operation plan of this feature. Here we have contouring. Since by default it is using a flat end mill, we have to change the type of the tool cutter. So we will go under the tool, and under the tool grip, we will select the ball nose, which have a radius of 3 mm and a diameter of 6 mm. Sorry, we will use the corner round type of end mill cutter, which have a radius of 3 mm. All right, so if we have to verify whether this type of tool will perform or not, we can visually see the tool on the screen, and we can adjust the outer radius, or we can go to evaluate, click on that fillet, and then find out that it has a radius of 3 mm, which is same for this tool. So we have changed the tool for this control milling operation. Now we will generate the tool path and then drag this one under the control milling section. So let's simulate the result and see what we get. We use the turbo mode, and There we go. Here we have the corner fillets. If we select the show difference option, so in color form, we can see the green color shows it is precisely what we have after machining, and it's completely matched with the CAD file. That is great. Now we have to perform the chamfering feature. For that, I will create the chamfer feature. Under the feature manager, right click the mill part setup under the 2.5 axis and then select the pocket. Since it is removing the material from the inside, so we have to select the pocket option and then select the edge. So the edge we have to select, we have two edges of the fillet, the bottom at the top. I think it's better to select the top edge of all of these pockets which have features at the top. We have also chamfer on the off-brown pocket and also at the bottom of that face. So once we have selected all the profiles, we'll go to the end condition. Here we will select the strategy fine. Since we only require one operation to complete the chamfering feature, and here we also specify the end condition of 3. I just selected the 3 number which is greater than 1. Since the thickness of the chamfer is 1, so we can specify the end condition any number greater than 1, which I will show you what would be the effect of that number. So it has generated the operation plans for all of these pockets, and we can see there are, I think, 6 or 7 operation plan. We can generate the tool path for these operations, and all of them are contouring mill operations. So since they are, we have to use the same tool, I will select all, combine these operation into single operation, and then go to edit definition and then select the relevant tool for this operation. So under the tool grid, we have the countersink, which have the diameter of 5 mm and it has an angle of 90 degree. If we divide 90 degree into half, we will get 45 degree, which would be the end result of our chamfer. So choose this one. So under the contouring tab, we have another option is called chamfering. So we will specify the length, what should be the thickness of that chamfer. It is 1. If you want to evaluate whether it is 1 or not, we can use the measuring tool and select the 2 edges of the chamfer. It will tell us what would be the length. Let's select these 2 edges, and it will give us the value of 1. So it means the thickness of that chamfer is 1. So, okay. One more thing is the clearance. I will use clearance 1 and then feature edges outer edge. Click OK, and then generate the tool path. Now the tool path has been generated and it's also being shown on the screen. We can simply drag and drop under the control milling section and simulate the result in a turbo mode. Here we can see the final result. And there we go, we have a chamfer at the top edges of the pockets. If you compare the result with the original CAD file and it shows in green color, it means it is perfect as required. So if you want to see the simulation in a tool mode, it will highlight the, it will also show the fixtures as well during the simulation. We can analyze the tools step by step, where it is moving, what type of machining operation it is currently performing. All right, so there we go. In the end, we got the chamfer. So the last part which remained for us was the hole that was not identified by the AFR. So let's create the operations to create this hole, as well as the tapping method to generate the, to machine the thread. So we will perform the same steps for as we perform for the rest of the operations. Since we are, I think in this video, I am also performing the pocket operations. All right, because there was some extra material left at the top of that face, which were highlighted in a blue color. So I will perform the machining operation firstly on the top face and then specify the height of that machining operation. So let's click the up to the face, and then we have selected the upper face of the boss. We will generate the operation plan. Here we go, we get the roughing mill operation only. So we go to the edit definition, and then we will change some parameters. Under the roughing tab, there is an option called allowance. And here it shows 0.25 mm. We will turn into 0 because we don't want to have any allowances between the machine part and the CAD file. So let's generate the tool path and then drag and drop under the roughing mill operation. So let's generate and then simulate the result under the turbo mode. There we go, we get the result, and then compare the result again and see if there is any blue region left. So we can see the top faces is completely green. All of the features have been created and it's perfectly as we require. We have some blue regions. One is the blue hole that we have to perform machining operation on it. So let's generate the operation plan. Under the feature tree, we have, we will follow the same steps. And now we will select the type hole. In the previous section, we selected pocket and boss, but now we have to select hole since it is a hole and it is a through hole. So I will specify the end condition as well to the bottom of this stock as the end condition. So it will machine that hole all the way from top to the bottom. So let's generate the operation plan for that. Here we go. We have two operations, one in the center drill and then second is a drilling. First, this hole will require a center drill and then it will be followed by the drilling operation. So we will generate the operation plan and then generate the tool path and then drag and drop under the center drill section. So all of the center drills are in the same section. We will combine them since we have only one center drill. So instead of using two operations, we will use a single operation for the center drill. So let's see what type of drilling options we have. So under the settings, we have a drill hole parameter, and there are various type of method to machine the hole. We have packing, we have drilling. So in case of drilling, the drill bit will go all the way down in a single step and then come back. So whereas in case of packing, just like a woodpecker, it will remove the material of depth of 2 mm and then it will retract back and then go back to the down and additionally remove the 2 mm of depth of material and then retract back. So it's called packing. So we'll select this type of operation for the drilling. So here we can see the drill bit, and we have to, everything is set up. The size of the drill bit is 8.5 mm since it is M and 10 times 1.5 and 1.5 is the pitch. So if we minus 10, if you minus 1.5 from the 10, we will get 8.5, which is the diameter of the drill bit. So once we have selected, we will generate the simulation and see the result. All right. So here we can see the hole is not being created all the way to the bottom, and the depth is specified here. So what we have to do, we have to override the depth and condition. So we can right click and go to the edit definition. Under the drill hole and under the feature option, there is an option here, override machining depth. Here I will add 5 or 6 more, so it will become 26 Let's regenerate the toolpath and then simulate the result and see whether the hole has been created all the way to the bottom or not. It's taking some time. All right, so now we have a hole all the way to the bottom, and all of these 3 holes are true holes. Now, during the simulations, we might have found that there were some extra material left at in the pocket area. It's better to completely machine down this pocket to the bottom, so that when we are moving the material from the bottom side, and there will be a good finish, and we won't require extra operation in only facing operation at the bottom. So let's create the pocket operation, which is all the way to the bottom face of the stock. So first we will select which operation is relevant to this one. It's a rough mill 10. We will open the settings, and then we will do the same procedure as we have done with the whole operation. We will override this machining depth and add some millimeters in it. If it is 6, we will make it into 10. All right. So let's press OK and regenerate the toolpath and then see the result. Here the toolpath has been changed as well, modified. We will do the same procedure for the control milling operation, which is also a part of this pocket operation. We will change the machining depth to 10 and then click OK. And now simulate the result in a turbo mode. All right, so now we have a pocket which is machined all the way to the bottom. Let's see the comparison with the CAD file, original CAD file. So we can see the green portion, everything is green, and there is no collision, and there is no extra material that is required. Instead, only the bottom plate is required, which require a different setup of machining operation. So for this demonstration, we have successfully created all the features which involve chamfers, pocketing features, perimeters, balls, round fillets, and it is exactly what we want in the final product. One more thing to go, which is the tapping. We have 3 holes, and these 3 holes are thread holes. It requires a tap operation which will generate the threads within these holes. So we already have hole features. What we can do, we can just simply go under the feature operation tree and then right click this setup, and then we have hole machining operation. Here we can select manually what type of operation we want for in the scenario of hole. So we'll select the tap feature. Since we have only 2 tap tools in our tool grip, it shows only 2 tools. So we will select the smaller one first for the small hole, and then select the relevant hole for that tab. And then in the operation, we can see the tapping that we are performing. So the dialog box will be opened automatically, and we can see the type of tapping, whether we want in a reverse direction or in a normal direction. We will also specify the setup definition for rapid mode or for clearance mode, so that the tap tool will not collide with the material of the stock. We will also specify the depth, since we want to create the thread all the way to the bottom. So we specified 26 mm of the machining depth. The feed rate and the speed we will use exactly from the library. Click OK. And here we have the operation. We will generate the toolpath for this operation. Okay, so we also have to do the same process for the second hole, since it also require a tapping process. So we will select the second tool, which have M10 times 1.5. So for that, we will select the bigger hole and go for the operation, and it is shown here as a tab. And the information related to this operation will be gathered from the technology database, such as the feed rate and the spindle speed. All right, so we don't have to change anything from here, just specify the setup definition in order to avoid collision of the toolpath with the material of the stock. Okay, let's click OK. Since we have override the machining depth, so we will generate the toolpath and see the simulation, the final result. So let's use the tool mode, in which we can see the simulation of the tool while removing the material. We are at the finalization stage, and it's very important to verify the simulation process at the end. So if we zoom a little bit, we can see during the simulation, there's some extra material left at the top of this face, which is quite thin walled. And this thing might happen in reality as well, that there will be a small material left at the corner, since we are performing the roughing operation in the middle of this face. So we can avoid such type of faults in our machining by changing the allowances under this roughing mill tab, roughing mill operation. So we will go under the roughing tab and then change the allowance from 0 to -1. So it will machine, and it will also machine the material which is outside the boundary. So there won't be any thin wall material left at the end. So it's like OK, and we can see that toolpath has also been changed. It has been extended in the output direction. Let's simulate under the tool mode to see the result. All right. So we have everything is being done, and the holes are also tapped, and they are shown in the red color. The reason they are showing in the red color is because these thread holes were shown only in a visual way, and in the CAD way there were no threads involved. So for such type of features, there will be some color differences. It might show in the red color. All right. As I have talked about the parameter, that it is performing the machining operation at the top of the face. And if we perform the simulation, we can see that first step is the facing operation, which is removing the material, and there is no redundancy in this step. All the steps have some purpose in this operation, but if we look at this operation, which is a rough mill operation for the parameter, it is moving at the top of the face, but it's not removing any material. So basically it is the redundancy and it's consuming time, which is not good for us. So we have to remove this redundancy, and after it complete the top phase, it start to machine down the side of the CAD file. So in order to remove the tool paths from the top phase, I have to remove the parameter feature and then create my own custom design parameter features. So let's delete this one, which was created by the AFR, and I will create my own parameter features, 2.5 axis feature. Here it is the open pocket. The difference between the pocket and the open pocket is in the open pocket, the tool is allowed to move freely and it's not closed between the boundaries. So we have to select the lower edge for the selection of the bottom face as a profile. So I will click the outer edge and it will automatically create a loop, which is the outer profile of this CAD file. Now I will specify the end condition. So the reason why in the default parameter setting, there were some tool paths at the top of the face was because of the end condition. The end condition was specified at the top face of the stock material, not on the current face of this CAD file. So in this situation, if we specify the end condition and the top face of this CAD file, it will not have tool path at the top face. So let's select the strategy rough and finish, and then generate the operation plan. And here we have rough mill operation and control mill operation which is in blue color. So let's generate the tool path. Here we can see again we have a tool path at the top of the face, which is the redundancy in our scenario. So we have to remove this one. We go to the edit definition, and then under the roughing tab, we have the option machine island top. We will uncheck this option, and now we will generate the tool path once again. Here we can see those tool paths which were on the top face are now gone, and we have the tool paths only at the sides of the CAD file. We'll specify the setup definition as well on this operation so that the tool will not collide with the material of the stock. We don't have to specify any machining depth, and then click OK. For roughing is perfect, and for contouring, we don't have to specify the top island, since in contouring operation it only perform machining on the sideways. Let's simulate the result and see what we have achieved. So here we can see in the second step, the roughing operation is not moving at the top of the face. It starts from the sides of the CAD file. So this is more efficient and timely productive. If we compare the result with the original CAD file, we are seeing everything is as we require. So let's say that we have generated the CAM operation, we have generated the tool path, we have spent almost 1 hour and 45 minutes on these operations. So what about if there are any change in the CAD design? How the CAM will understand that changes? Or do we have to start all this process from zero? So this is very important in terms of software, whether the software has such capability or not. If we are importing the file from the outside, and then we might have to restart the machining process. But if we have designed the CAD file within this SolidWorks, and if we make some changes in that design, and the SolidWorks CAM will understand these changes and will generate the operation plan accordingly. So we don't have to start from the beginning. So let's say this is the CAD file and we want to change some of the dimension on these CAD file. So let's change the radius. So if we change from 28 to 25, the it will affect 3 or 4 features. We can see the thickness, these two holes, these two round bosses have been, the size has been reduced, and it's also affected pockets as well. So if we jump back to the cam, it will alert us and it shows there are some changes. If we are agree with it, we can click yes. And then if we go to the feature tree, it will show also that we have to regenerate the toolpath because it identifies the changes in the CAD design. So we will let it to regenerate the toolpath and then see how much manual work we have to perform, or what additional features we have to add or we have to remove. So give it some time, since it's redoing everything from beginning till end by itself. All right. So if we go to the operation tree, we can find everything is as we left and nothing has been changed. And it also generated the rough mill operation for the change of that pocket, also the relevant control mill. So let's check the result in the simulation. So if you go in the turbo mode, we will see the final result. And then if we compare with the original CAD file, we can see that it has updated the tool paths, and it has performed the machining operation based on the new requirements, and is perfect as we want. There is no undercut, no overcut as well. So this is one of the greatest feature of SolidWorks CAM. If you want to, it's better to use the SolidWorks to design the CAD file and then perform the machining operation in the same software. So at this stage, we have finalized almost 90% of our work, from face milling to roughing to control milling to center drilling and tapping, and how to create chamfer, how to make roughing operations. So everything has been completed at this stage. But one little information that I haven't shared with you guys so far is the machining parameters, about the feed rate, about the spindle speed, the depth cut, the allowances, the side parameters. So let's talk about that one right now. Let's say we have a rough mill and it has a tool path as shown on the screen. So under the roughing, we have options such as pattern. We have various options. We have pocket out, in which the tool will start to machine the material from the inside, and step by step it will go to the outer boundary. So this is what it was selected as a default. We can select other options, pocket in, and in this situation it will remove the material from the outside first, and then it will go step by step toward the inside of the material. We have some other options like spiral in. It will perform the machining in a spiral way. We have control milling. We have a volume mill. In SolidWorks CAM, we have more volume mill option, in which it will generate the tool path, which is productive and time efficient. So let's see whether it is time efficient or not. We will select the pocket in type of feature. generate the tool path, and then under the optimize tab, we have a time here, which is specified. So in order to achieve the machining operation of this specific selected one, it will take almost 12 minutes. So if we change the pattern to volume mill, it will generate the volume mill toolpaths, which would be time efficient and productive, and which will be also good for the tool life and the machine performance. But there are sometimes there are some limitation to this type of pattern. As we can see, it's not removing the material close to the fixtures, maybe because it's colliding with the fixtures. That's why, and it's taking time 9 minutes, which is less than 12. But since it is not removing other material which is closer to the boundary, we can say that it's almost same as pocket in. So I will select the, yeah, here we can see the tool paths in case of volume mill. The way it has been generated, if it would be a little bit further, it might collide with the fixtures. Okay, so let's see how much time it takes for the spiral in type of tool paths. We will click preview, and we have a different tool path. It is in the spiral way. If we go and see the time, and this operation will take 36.9 minutes. It will take maybe 2 times more than the previous type of patterns. So for us, we will select the pocket in type of pattern, and see it's taking only 12.9 minutes. So we'll select this one and click OK. Okay, along with this pattern, we have some other options, like for the depth parameter. In the depth parameter, we have options like first cut amount and the maximum cut amount. And let me show you the side view of this part. We can see the green color lines. These are the tool paths, and we can see the steps as well. And the distance between all of these steps is same, which is 50% of the tool diameter. So if I change the first cut to 25% of the diameter of the tool, the first cut will move a little bit closer to the up face. And the rest of the depth cuts are same as 50% of the diameter of the tool. So let's change this one to 25 as well, and we can see more tool paths have been generated, since it is removing the material step by step, and in each step it is removing a small portion of material. So we will require more tool paths steps. So let's go to the top view, and here we can see the tool path in the sideways. So if here we have allowance which shows 0.25, it means that this operation will not remove the material by 0.25 millimeter from the boundary, since it is a roughing operation. So in case of step over, we have 40% of the diameter of the tool. So let's, if we increase the this number from 40 to 60, and there will be fewer tool paths in the sideways. So let's change to 60, and then preview. And here we can see we have tool paths, and they are now fewer as compared to previous one. So if we decrease the step over from 60 to 25, we will have more tool paths, and it will remove the materials and with small portion, and it will take some steps to complete the complete machining process. So we can also see how much time this operation will take, which is taking 42.25 minutes. So all of these parameters have a direct impact on the time of the machining. So we will have to select the parameters based on the type of the tool we have, and to how much fast we can perform the machining. Here we have other cutting method. There are two methods, climb and the conventional one. The conventional one is the one which is used in the manual milling machines. And what it does, it rotate the cutter in a direction which is parallel to the direction of the feed rate of the workpiece. If we select the climb option for the cutting method, we will have the direction of the cutter in a direction which is opposite to the direction of the feed rate of the workpiece. Okay, so now it's time to finalize the process by generating the post code. We have to perform the machining operation. Once we are sure that machining is accurate and there's no collision and there is everything is as what we require, we can go for the post processing. Okay, guys, sorry for the pause. The time is also up, and let me wind up these presentations. I will just talk about the post processor. Once we have finalized the machining operation, it's time to generate the post processing. Here we have the icon, and we will press this icon, and then we will have to specify the location where that text file of G and M codes should be. So I will specify the location on the desktop and then save it. And if I want to change the name, I can also change the name. So let's code file for cam part. All right. So let's save it. So here we have some option. If we play the button, it will start to generate the G and M codes, which will be according to this Fanuc controller, which is Fanuc 16M. All right. So under the option, we have, if you want to open this G and M code in the NC editor window, we can check this option as well, and then play the post-processing process. So check this one and play it. It's now generating the G and M codes according to the operation and features we have created. It will take few seconds to, and all right, so we have the size of that file as well, which is around 113 KB. It's a quite small size, and it is in the text format. So it will also be open, this code will also be open in the NC editor, in which we can make changes in these codes if there are any. All right, guys, thank you so much for your time, for attending this webinar of 2 hours. I hope you guys have learned a lot from this webinar. And let's have some question and answer session. Let's see what type of questions we have. All right. So here we have a question. Can we design the milling tool, customized milling tool in the server SCAM, and then use it along with the tool holder? Yes, in server SCAM, we can design any type of tools for both milling and turning operation along with the tool holder. And then we can, if once we have designed, we can insert that type of tool in the technology database of this SolidWorks SCAM, as I have also shown in the technology database. So I hope this have answered your question. So the next question is, All right, can we check the machining standard while performing the CAM programming in the server CAM? The machining standard. What I understand from this question is talking about the tolerances that is required for the machining, and also some, yeah, there are some machining standards, like how much depth of the cut we have to take. So these type of things we can analyze as well in this SolidWorks CAM. But there's another add-on which is called CAM work, which is used for the advanced machining. So it's also allow us to generate our own standard of machining and then verify the CAM operation and features accordingly. There's another information question. The code generated can only work with the defined controller, or can we change it according to the controller we have? Yes, these codes are relevant to the type of controller we have in the CNC machine. If the CNC machine have a FANU controller, we must have a controller and these codes generated according to it. If we have Mazak controller or a Haas controller, we must generate codes and that is relevant to that controller. All right. So I think that's all for this webinar. Um, Thank you so much for your time. And inshallah, those of you guys who have attended this complete webinar of 2 hours, we will send you guys the certificates. With the help of that certificate, you guys can redeem the CPD points of zero point 0.5 from the Pakistan Engineering Council. Thank you so much. Assalamu alaikum wa rahmatullahi wa barakatuh.